Welcome to AP Chemistry. We continue our discussion on chemical kinetics by focusing on the purely mathematical portion of our unit in reference to rate laws. So far, we have worked with differential rate laws, relating the instantaneous rate at a given point in time to the concentration of the reactants. We will now use these to create integrated rate laws, which will relate the concentration of those reactants to a given point in time. We review the notion that with differentiation, we are not finding an average rate or average slope, but rather we are finding an instantaneous rate, an instantaneous slope associated with a given point in time. Taking our sample differential equations at the top, we can rearrange them into the form below. The point of showing multiple equations here is so that you might see the symmetry in our general operation. We can further rearrange them algebraically. At this point, we still have not performed any calculus yet. Now we can take the integral of each of these functions. Think of us taking all of the tiny differential pieces and putting them together over a certain given area provided to us. The result of the integral gives us a difference over a certain region. Each difference looks slightly different due to us starting with a different order, but it's important to note how similar the functions are in relation to each other and in relation to their original differential rate law equations. Finally, each of these equations can be rearranged into a linear form, as shown by the zeroth, first, and second order integrated rate law equations. The importance of these equations comes in reference to analyzing data. We begin by looking at graphs of our differential rate law equations, that is, rate as a function of concentration. Notice how the zeroth order rate law is not dependent upon concentration. Its rate is constant, equal to the rate constant K, and not dependent upon any difference in concentration. For negative orders, rate is inversely related to concentration, and for positive orders, rate is directly related to the concentration. Furthermore, as the order changes, the rate is related exponentially to the concentration. Note carefully the connection between the previous graphs and these. Concentration is a function of time. For zeroth order equations, the slope or rate is constant at any given point in time. However, the graphs for negative and positive orders differ significantly. Now, with these graphs, if we apply the form of the integrated rate law equation to the correct order of reaction, we will get the form of a linear equation on our graph. Notice how for a zeroth order function, only concentration versus time will give the form of a straight line. But for a first order function, only the natural log of the concentration versus time will give the form of a straight line. And for a second order function, only the reciprocal of concentration versus time will give the form of a straight line. The purpose of these relationships is so that when we are given particular data sets, the order of the reaction might be deduced and the rate law can be determined. One last set of equations that we will derive is associated with half-life, the time it takes for a reaction to arrive at half the original concentration. Since at time half the original concentration is half, these equations may easily be derived by substituting in for concentration at time t 0.5 times concentration at time 0. Rearranging, we can get the final form for each. We should note that the half-life for a zeroth order equation is directly related to concentration. That is, the greater the concentration, the greater the amount of time will be required to reach half the original concentration. But for first order reactions, the half-life is constant and not dependent upon concentration. This is a very convenient way to determine first order reactions if their half-life is shown to be constant. Finally, second order reactions have a half-life inversely related to concentration. That is, at higher concentrations, the half-life will be smaller, but at lower concentrations, the half-life will be longer. Again, this is due to the greater number of particles required for a successful collision to occur. Till next time we consider the mysteries of the absolute, Crip.